we learned about the Hilbert transform. Which was defined like this: h of f x equals, in the principal value sense, integral of f of x minus t over t. I'm always forgetting this constant. Over t like this, over the entire real line. And we learned that this thing actually makes sense when f, so makes sense or converges. So limit converges. Not so bad. When we have f in compact support and we took c infinity, but one derivative was enough. Okay, and it had various nice properties. It behaved well with respect to translations, with respect to dilations. And you can think about this as a kind of one, well, you can think of the Bernoulli transform as a two-dimensional version of the Hilbert transform, because the kernel on the Bernoulli transform is exactly blowing up like absolute value of z squared, right? So it's exactly failing to be integral by itself, just as this kernel is failing to be integral by itself. But nevertheless, in the Bernoulli transform, we were able to show that it does exist in the principal value sense, as we can for this guy. And the missing part of the proof of the Stoylov decomposition was, again, that we wanted the Bernoulli transform to be bounded in LP, where the LP norm goes towards 1 as P goes towards 2. And what we're going to do today is we're going to show that the Hilbert transform has an LP norm, which is firstly going to show it's LP bounded, and we're going to show that its LP norm tends towards 1 as we tend towards 2. Okay? If you read Wikipedia, you can read more things about this thing. So this thing is something called a Fourier multiplier. It's something that we can understand by taking the Fourier transform of the function, multiplying by a nice bounded function, and Fourier inversing it. And these things are easy to show that these things are bounded in L2. So there's actually an isometry in L2. Actually, it's analogous to the analysis of the Bernoulli transform, which was an isometry in L2 as well. But we're going to skip all that stuff. We're going to go straight to try to show the LP boundedness. And that's a key step in actually showing the LP boundedness of the Bernoulli transform. So I'm going to use the method of Alford, explained in Alford's book, Crazy Conformal Mappings. However, the actual proof for the Bernoulli transform is pretty technical. So this proof already is fairly technical and computational. So I'm probably just going to outline the proof for the Bernoulli transform and not go into the full details of it, because it will take maybe 2.5 classes to fully prove it. And so think of this as a kind of a flavor of the techniques involved. So ultimately, we come down to understanding LP boundedness property of single integral operators. And my hope in doing this is to try and motivate why single integral operators are interesting and why people care about them, and why why so much work has gone into understanding the LP boundedness properties of them. Okay, so let's get going. So the theorem I'm going to show is that H is bounded in LP. And if CP is the norm, LP operator norm of operator i.e. if we have that H of F in LP is less than or equal to CP, like this, then CP tends towards 1 as P tends towards 2. That is our goal. So let's get into it. Proof. So our starting point is this formula that we established yesterday or on Monday, which was this following identity, which has a name associated, the name I cannot pronounce, and also won't be able to spell, so I'm just going to ignore that part. So y minus x plus I epsilon dy, and this was equal to f of x plus the Hilbert transform of f of x over 2, like this. So this is what we established on the previous class, and this too was essentially a computational fact that we computed our way through, and this will be kind of a key thing for us today. So we're going to study the following mapping. So we're going to define f of x0, y0 to be this guy, 1 over pi, equal to minus infinity to infinity, f of x, x minus x0 plus I times y0, like this. Okay, so this thing, we're gonna, first observations, this thing is a holomorphic function in the upper half plane, also in the lower half plane, but we're only caring about it in the upper half plane, right? Because we're just integrating something. If you just look at this thing on the bottom, it's a nicely holomorphic function. We're integrating with respect to x. That's not going to mess things up. We can differentiate through. The complex derivative will exist. So this thing is holomorphic in the upper half plane, and we're going to use that property in a crucial way. Okay. So we're also going to write it like this, as a u of x0, y0 plus v of x0, y0 for these two functions u and v. Okay, so let's just note holo on C plus, which is the set of z belong to C, such that the imaginary part of z is bigger than equal to 0 or bigger than 0. Okay. All right, and this is somewhat close to this formula, right? If we mess around with this formula a little bit, let's multiply by 2i on both sides, and then what do we see? We'll see that, let's just do it here. So if I multiply by 2i, then I get rid of this thing. And then I have a 2i coming up here. Right? And then, oops, and I missed out what this should have been, the imaginary part of this, right? Yeah, so then what happens here, then we're going to get minus h f of x plus I times f of x, right? So what does that mean? That means that from this formula, let's call this thing star, we have that the limit as y0 tends towards 0 of this function f of x0, y0 will be just exactly, this thing right here, right? So it'll be minus h of f of x0 plus I f of x0. And that's also the limit as y0 goes towards 0 of these two guys, u of x0, comma y0, iv of x0, comma y0, right? So in other words, what we have is that limit as y0 goes towards 0 of u of x0, y0 will be this minus the Hilbert transform f of x0 like this. And the limit as y0 goes towards 0 of this guy will be our function f of x0. Yeah, like that. And since our goal is to show that the Hilbert transform is bounded in terms of this function f, so the LP norm of this thing is bounded in terms of this thing, and get control of what constant we have in front, what we're going to do is we're going to get a relationship between the integral of the u component, or the pth power of the u component, and the pth power of the v component of our function f. Okay, and we're going to use the fact that f is holomorphic to establish this thing, and it'll ultimately, the calculation comes down to using divergence theorem and decay properties of the derivatives of this thing. So the proof is actually kind of neat, but it's heavily computational. So we need to start to compute some stuff. So what do we start with? Let's start with the following thing. Let us take the Laplacian of these coordinates and calculate. Now let's take the Laplacian of the pth power of u and v. So let's underline this, because now we're going to start to calculate quite a bit. So calculation. So we're going to calculate the Laplacian of the pth power of this, and the Laplacian of the pth power of this, and the Laplacian of the pth power of f. And we're going to show that the Laplacian of the pth power of f minus a certain constant p minus 1 over p, or the other way around, p over p minus 1, the Laplacian of pth power of this is always going to be positive. And the point of that is that we can then apply the divergence theorem to the Laplacian of that expression and get a relationship between the pth power of this and the pth power of that. So this is where this is going. So you're going to have to just watch me calculate stuff for a little bit, but that's the goal. All right, so let's get into it. So if we take the first partial of the pth power of u, then that's not too hard, then that's p. Go to p minus 1, and then we differentiate this absolute value, so we're going to get u over absolute value of u, and then we get u of x like this. Yeah, so this is just the chain rule applied to three things, right? The outermost function is power p, the second outermost function is the absolute value, and the innermost function is u. Yeah? So that's what we get, and we can write that as p over u to the p minus 2 times u to the x. Yeah? And then let's take the second derivative of this thing. And then what happens, so let's first apply it to the first term here. So we're going to have p minus 2, p minus 3, and now the same thing. We're going to have now u and then u of x squared, because when we apply the chain rule to this thing, we're going to get these two guys coming out again, right? And now we apply it to this stuff. So we're going to have p u to the p minus 2, and then we're going to have u of x squared, and then u of x, like this. Yeah? Everybody happy? Cool. All right, so since this expression is important, I'm going to run off some board space. If we do this with respect to y, then we're going to get a completely identical expression, except we're going to have u of y x. So again, we're going to have u of y here, and u of y squared, and u of y, right? This is, this will be exactly the same things, right? So if we do this together, the Laplacian of the pth power of u, then what are we going to get? Then we are going to get this kind of stuff here. So we're going to get p minus 2, u to the p minus 3, and then we're going to get this u squared term. And then from this thing, we're going to get u of x squared plus u of y squared, like this. That's what happens from this thing. And then if we do this thing, we're going to have p u to the p minus 2. And this contribution here will just be u of x squared plus u of y squared. And then we'll also have this thing here, which is u, and then it's going to just be Laplacian of u itself, like this. Yeah? Just adding up the second derivative with respect to y and the second derivative with respect to x and putting them together, that's what we get. Yeah? But u is actually a coordinate function of a harmonic function, right? Taking y0 to be positive, so it's in the place where it's holomorphic. So the Laplacian of u is 0, so that term just drops out. Yeah? So we can just get rid of this term, like this. And then we have this expression here. And then we are in a position to put this all under the same kind of powers, because this thing now becomes p minus 2, right? So let's write this p minus 2, u to the p minus 2. Better. And u of x squared plus u of y squared. And then this term right here plus p u to the p minus 2 of u of x squared plus u of y squared. And then we can factor this stuff and put it into here, and our final expression will be this p minus 1, right? Because we're going to add another p to this. And then u of p minus 2, and then this thing u of x squared plus u of y squared, like this. Yeah? Everybody happy? Thumbs up if you're okay. Yeah? Cool. And if we do this for the y coordinate, then we'll have something extremely similar, because this calculation didn't use anything specific about u except that it solves the Laplacian. So if we do this for y, y for v, then we're also going to end up with this expression p minus 1, v to the p minus, and then v of x squared plus v of y squared, right? But our function u and v are holomorphic, so they satisfy Cauchy-Riemann equations, right? So Cauchy-Riemann equations again, u of x equals v of y, u of y equals minus v of x. But when we square it, we don't notice. So we can replace this expression here by u of x squared, u of y squared, right? So this is p minus 1, v to the p minus 2, u of x squared, and u of y squared, like this. Yeah? Cool. All right, I'm going to raise the board, and now we're going to calculate the pth power of the Laplacian of the pth power of f. Let's take the x partial of the pth power of f, which will be the x partial of, we're going to think of this as u squared plus v squared to the p over 2, like this, right? Because f has is a complex valued function with the real part is u, the complex part is v, so the absolute value of f is u squared plus v squared square rooted, so this is the right thing. Yeah? So then if we differentiate this, then what happens, we're going to have p over 2, we're going to have u squared plus v squared, and we're going to have p minus 2 over 2, and then we take the partials of this stuff, we have u of x plus 2 v of x, like this. Yeah. All right, let's do calculation second time. Okay, so we're applying it to this, so we're going to have p over 2, p over 2 over 2, and u squared plus v squared. And now we're going to have p minus 4 over 2. And then differentiating inside, we're going to get this thing again. So we're just going to write 2u of x plus 2v of x squared, right? So that's putting the derivative on that part right here. Now we differentiate this stuff. So we're going to have and if we differentiate this stuff, we're going to get, putting the derivative on the first term, we're going to get 2ux squared plus 2 v of x squared, like this. And then putting the derivative on the other thing, we're going to have uxx plus 2v vxx, like this. Everybody happy? Yeah? So if we do the Laplacian of f to the power p, what's going to happen? We're going to have this kind of term at the front, so this, p over 2, p minus 2 over 2, and then u squared plus v squared, p minus 4 over 2, and then we're going to have this kind of thing, 2u of x plus 2v of x squared, but now we also have 2u of y plus 2v of y squared, right? And then contributions from that stuff. So let's put it on the line here. P over 2, u squared plus v squared. This. And we're going to get 2. Let's just put it at u of x squared plus u of y squared. It's 2 v of x squared plus v of y squared. And this term will vanish because this thing will be 2u of x, u of the second root of x plus the second root with respect to y. It'll be the Laplacian term of u. And the same for this thing. Yeah? So these guys will just disappear when we add the second root of respect to y of this thing to the second root with respect to x of this thing. You know, the same kind of way it happened before. So this thing just vanishes, and this is the guy we are left to play with, right? And we can make some instant simplifications because we know that, again, the Cauchy-Riemann equations, u of x equals v of y equals minus v of x. So then this thing we can just turn into u of x squared plus u of y squared. Yeah? So I'm going to erase this and just put a 4 right here because there's 2 of them, right? Like this. Yeah? And then this guy we have to look at a little bit more closely, and what we're going to find is there's a whole bunch of cancellations. So let's give this thing a name and let's expand it out. Let's call this thing star. So star. Let us pull out the 2's from everything, so that's going to be a 4 in front of everything for us, right? So we're going to have a 4. And then we're going to have this stuff squared, so we're going to have u of x squared, v of x squared, and then this mixed term, which will be 2u of x, v of x, right? That's from spanning that stuff out. And the same kind of game for this. So we're going to have u of y squared, and then v of y squared, and then the mixed term, which will be 2u of y, v of y, like this. Yeah, everybody agreed that that's what star is. Yeah. Okay, so we have Cauchy-Riemann equations which tell us that if we want to turn this stuff into partials with respect to x, then what happens then? V of y, this is now u of x, but u of y is minus v of x, so this guy becomes, let's put it this, minus v of x. Yeah? But then if we look at this expression here, then this thing will be is exactly the negative of this thing. So these terms will cancel out. This cancels with this. Yeah? So what we have is this stuff. And let us pull out the u squared from this thing, and we're going to have 4 of u squared, then u of x squared plus u of y squared, like this. And let's pull out the v squared, and we're going to have v of x squared plus v of y squared, right? But now again, we're going to use the Cauchy-Riemann equations to turn this into stuff about u. So then this is going to be 4 of u squared. Actually, let's do this in one step. Let's get fancy. So it's going to be u squared, v squared, and then we'll have u of x squared plus u of y squared, like this, turning this thing into this thing turns into u of y squared, and this turns into u of x squared. Yeah? Everybody happy? Yeah, so this expression star now simplifies quite a lot. Yeah, now simplifies quite a lot. My lines are a little bit running into each other. Let me put some kind of divider. Between these calculations. So this is the calculation for the Laplacian of f to the p, and this is the calculation for this expression star inside it. Okay, so let's now put in the simplifications we have. So Laplacian of f to the power p, like this, is now p over 2, p 2 over 2, like this. And we are going to get this guy right here, which will contribute a power of 1 to this. So this guy here now becomes p minus 2 over 2. Right? And, oh, we have a 4. The 4 will kill this a half and the other half. Right? And the only thing remaining is this thing, u of x squared plus u of y squared, like this. Yeah, so that's what we get from that thing. And now we add this thing to it. And what do we have? Plus, so this 4 will turn this into a 2p of u squared plus v squared, p minus 2 over 2. And again, this u of x squared plus u of y squared. And then we can put stuff together because we have a minus 2p of this stuff and then a 2p of this stuff. So this thing nicely simplifies to just p squared of u squared plus v squared p over 2, like this, u of x squared plus u of y squared, like this. Everybody agree? Yeah? And recall when we did Laplacian of u to the p, we got a similar expression, except we had p minus 1, and then this u squared plus v squared, p 2, and then, go ahead. Okay, so what this means is that, so let's call this thing star star, is that if we consider, so if we consider Laplacian of f to the power p, and let's multiply this power of p of u by p over p minus 2, sorry, p over p minus 1, like this, then this. So that is what we want, because this expression here is definitely bigger than this thing right here. Yeah? Yeah? Everybody happy with that? Thumbs up if so. Everybody give me the feedback. This is a long calculation, I agree, but I want to keep you guys with me. No, because that was my initial thing. So look, if we look at this expression right here, so this term here factors. All right. Okay, totally good. Right, so the Laplacian of this thing is a positive function like this, yeah? And we are going to use that in the following way, because we know that the Laplacian is just the divergence of the gradient. Yeah. So recall. So if we want to, well, so recall. Laplacian is equal to the divergence of the gradient, like this. So we're going to consider this as the divergence of the gradient, and then we're going to apply the divergence theorem on a particular domain, which we're going to let tend to infinity. So take omega of r to be this shape here. So it's the set of z such that z is in the upper complex plane, c plus, and mod z is less than capital R. In other words, it's just this half circle like this, right? 0 to r, capital R. And so this is our omega of r. And we are going to apply the divergence theorem to this expression, and we're going to have that it has to be a positive quantity, right? So we know that 0 is bigger than or equal to 2, the integral of omega of r of the divergence of the gradient of this thing, f to the power p minus p over p minus 1, u to the p, like this, right? Okay. And then we're going to apply the divergence theorem and then integrate this stuff on the boundary, right? So this is the same as the integral around the boundary of this region of the gradient of this expression f to the p. It's p over p minus 1, u to the p, like this, with respect to h1 measure around, dot product with the outward pointing unit normal. So we're going to write tau for the outward pointing unit normal to h1 of s. So tau points outwards, so this is tau like this, and it points outwards like this. This is just a statement of the divergence theorem. Yeah? Cool. So how this is going to work is that when we look more closely at this thing, then the derivative dot producted this part of the circle here is actually going to vanish, because this function f is a holomorphic function, and just from its expression, actually it's not to do with it being holomorphic, just from the expression, just from how we came up with it, we're going to see that the derivative of f just decays as we go out towards infinity, and f also decays. So it decays fast enough, it's actually going to decay like 1 over r squared, so that the contribution on this side is going to be 0. Okay? So that means the only contribution will be along this side, and that will mean that we'll have the derivative dot producted with the outward pointing unit normal on this side, which is minus e2, right? So it'll mean we'll have the y derivative of this expression, the negative of the y partial of this expression will be all that we have left, okay? And then from that, we'll have an expression about the way that this thing changes with respect to y, and we'll be able to get a relationship between f and u, which is ultimately our goal, because we have that the coordinates of f are our initial function and a Hilbert transform, and we're going to try and control the Hilbert transform in terms of the function f. So that is where this is going. Okay, so let us actually maybe squeeze some more things into this board here. Now let me just erase the board, and we'll do this extra stuff. So what did we have? We have that 0 is greater than or equal to the integral around the boundary of this region of the gradient of this expression f to the p minus p over p minus 1, u to the p, like this, dot product the outward pointing unit normal, like this. That's the thing we had to work to obtain. Okay. Now let's recall what f is. F of x0, y0 was this expression. We're integrating like this. We're going to have f of x, and then it's x minus x0 plus I times y0, the x, and there's some constant in front, which I think is 1 over pi. Let me check. Yeah, that's the constant. Let me write the integral better. Okay. Now, what happens as we let y0 tend towards infinity? Well, this thing on the bottom will get bigger and bigger, so this this function will tend towards 0 as y tends towards infinity, right? And it's a holomorphic function, and when we differentiated this, it's, you can also anticipate the derivative go down to 0, but we can just see it directly from the calculation. So let's take the partial with respect to x. So notice that if we take the partial f of x0, y0, then everything is smooth. Our function f is c infinity. We're going to differentiate through this without problems for that reason. We're going to have 1 over pi, and then we're going to just be differentiating this thing with respect to x0. So we're going to have f of x over x minus x0 plus I times y0. And we're going to square this expression, and then we differentiate this internally, and we just have a minus sign like this. Just chain rule. And if we do this with respect to y, or y0, it's a similar kind of thing, right? So we put it down here, 1 over pi. Yeah, so when we do, so it's the chain rule. So when we differentiate the internal function with respect to x0, then we're going to get a minus. Oh, I see what you're saying. So there's minus, minus. I get it. You're right. Good. Thanks. And then let's do this guy. So we're going to get the same thing, the minus minus will cancel, so we'll have this, then we'll have x minus x0 plus I y0, everything squared, and now we're just going to get an I right here. Yeah? And the point about this is that when we take the absolute value signs throughout, then as we let x0 and y0 tend towards infinity, then f has got compact support. So this thing here is this x, the non-zero x are only going to be for the compact support of f. So this is f, and it's got a compact support like this, right? So as we let x0, y0 tend towards infinity, then this x minus x0, y0 in magnitude is something like x0, y0 absolute value, yeah, for all x0, y0 which are large enough. Yeah? As always, if you have to leave, then leave. Yeah? So for some constant c, which depends on the function f, depending, we don't actually care that it depends on f because we're going to let r tend to infinity and everything, and this dependent will vanish. We have that the absolute value of the gradient of this thing, of x0, y0, is less than or equal to some constant over x0 plus I y0, absolute value squared. Yeah? For all of these guys which are big enough, for all x0 plus I y0 bigger than, say, some r0, for some, and some r0 bigger than 0. Okay? We have that this will be true. Yeah? So when we do this integral around the semicircle of radius r, yeah, in this part of this guy, then we have that the f itself is certainly bounded, because f is bounded and it's actually decaying as we let y0 tend towards infinity. Yeah? y0, x0 tend toward infinity. So when we take the derivative, we'll have a term to do with f, we'll have a gradient with respect to f, and this guy, the same story holds true. This is just one of the components of f, and the gradient will decay quadratically. Yeah? So putting this stuff together, we'll have that the limit as r goes to infinity of the absolute value of the boundary of this guy, take away the real part, this thing will tend down to 0 as r tends to infinity, because the perimeter is of order r, but this thing is decaying like 1 over r. Oh, sorry, like this thing is decaying like 1 over r squared. Everybody happy with that? You guys happy with that? Yeah? So in the limit as r goes to infinity, then this integral right here, let's call this thing star, or star star. No, let's call it star. We haven't used it yet. So from star, we will just have the integral with respect to minus r to r, but the outward pointing unit normal in that case is just minus E2, right? So then it'll be the dot product of the gradient with minus E2, which is just minus the partial with respect to y, right? So letting go to infinity, we're going to have that 0 is bigger than or equal to the integral from minus infinity to infinity of minus the partial with respect to y of this stuff. I should probably say y0 because I'm defining this with respect to y0, so let me do y0. like this. And this is just integral, I guess integral with respect to x0 like this. Yeah? And now we're going to take the derivative out from this integral, which I claim we can do again because of the smoothness of everything. Right? Because of the smoothness of everything, then this thing is like saying minus d by dy0 of this integral minus infinity to infinity of f to the p minus p over p minus 1 u to the p x0. Yeah? Cool. So let's rewrite that. So that's the same as saying that 0 is bigger than or equal to this thing. The x0. Yeah? Everybody happy so far? Yeah? Okay. But the claim is that this guy, this entire guy, again, is going to go towards 0 as we let y0 tend towards infinity. And that's not hard to see, right? Because if we just multiply this guy by the complex conjugate, then we're going to get the absolute value of this thing times that thing up there. So I'm over time, so let me just finish with that. So note the limit as y0 tends to infinity of f of x0, y0 is 0 because, let's just mess around with it here. So if we just multiply this by x minus x0 plus I of y0, and then like the complex conjugate right here, x minus x0 plus I of y0, right? Then this expression here is like the absolute value of x minus x0 plus or minus y0, doesn't make a difference, squared, yeah? And then this thing over this thing is of order of this thing, and then as we go towards y0 goes to infinity, then it decays. Yeah? Are you guys happy with that? Yeah? So this is true for y0, and u is just a component, sorry, this is true for f, and u is just a component of f, so it's also true for f. So because of, let's call this thing star star. Yeah? And so the limit as y0 goes to infinity of this guy is also going to go towards 0, right? So we have that this entire integral as y0 goes towards infinity is tending towards 0. Yeah, it's tending towards 0. So think about this just as a function of y0. As we go out towards y0 going towards infinity, right, this y0 goes towards infinity, then this thing is going towards 0, right? But the derivative is also negative, right? The derivative is also negative. So just thinking about this thing as a function of y0, it has to be doing something like this. It has to be going like this, because the limit is 0 to infinity, which means in particular this thing will be positive. This thing will be positive for all y0. Yeah? Are you happy with that? Yeah? So, integral of this thing, f the p minus p over p minus 1, u to the p, the x0. So this thing is a function of x0, y0, so is this, and we're doing it with respect to x0. This thing will be positive for all y0 bigger than or equal to 0. Yeah. And what we're going to do is we're going to let y0 tend towards 0 so that f will recover and as its coordinates the Hilbert transform of f and f itself, and then messing around with this relation will ultimately give us the bound that we want. Okay, so but that'll take another 10 minutes, which is more time than I want to keep you. But this is how this proof is going to go. It's kind of a technical calculation, but yeah, that's sometimes how things have to be done. The original ideas were not like this, but after years of development, people find a way to just directly calculate it from some initial expressions that they cook up. So you cook up this f and look at this expression, and then ultimately you can get a rather direct proof of this boundedness of the Hilbert transform. All right, so that is what we'll finish up on Friday. If you want a fun exercise, try and do it yourself. Try from this inequality, using Holder's inequality, to prove the thing that is claimed. It's not that far away. And after we complete that, I'll give you a bit of a sketch of how from that we can get the LP bound on the Burning transform, and then that'll be the single integral part of this course completed. All right, everybody happy? Any questions before we sign off? All right, pleasure. Right, see you guys all on Friday. Bye-bye.